Hey guys, this is 23.4 through 23.6. Some very cool things we're learning about light right now. First, obviously we know light is it travels as an electromagnetic wave and travels at theoretically the speed of light, which is roughly speaking right here. Whoops, not what I said. Dang it! Oh, I got to get back and delete a few things and. Let's go back to draw, and let's erase this. All right, get rid of this stuff from our ray diagrams. All right, come back down to where we're working today. Man, I didn't mean to push that button. All right, when it comes to total internal reflection, first thing we need to understand, speed of light is going to be represented by the letter C, and while it is 2.9979248 times 10 to the 8th meters per second, let's just use 3 times 10 to the 8th. So 3e8 is how you're going to typically see me write it. Now, we have what's called an index of refraction. And an index of refraction is basically telling us how well light travels through a material. Okay, an index of refraction will always be greater than 1 because to find it, we take the speed of light divided by the velocity of light in that material. Now, speed of light is in a vacuum, right? So out in outer space where there's nothing, we'd have it traveling at 1. In air, at standard temperature pressure, it is 1.0003, but because that's variable depending on temperature and pressure and things like that, air density, we're going to just assume that air is 1. It's not perfect, but it gives us a pretty good estimation there. And then you can see that in water, N is 1.33, different kinds of glass, lucite or plexiglass is plexiglass, diamond is 242, and that's why diamonds tend to sparkle. It slows light down so much that the light literally tears itself apart. Different wavelengths will separate. Prisms do that. Things like that. Okay, so this is the first thing you need to understand is when you're trying to talk about the index of refraction based on speed or velocity of light in the material, this is a table that we can go to. It's here on page 642. And you can see the formula. It's pretty straightforward. N equals C over V. Or C equals N times V. Or V equals C over N. You can rewrite this in so many different ways. All right, let's erase as we go. All right, so there's our first piece of information that's useful to us. Then we have Snell's law. And this is the law of light refraction. This is what happens when you put a pencil into water inside of a glass jar and you notice the pencil looks bent. The reason that's happening is because the light is changing speeds. And as it changes speeds, it is bent or refracted. All right, so a couple of things we really got to get super specific on. We're going to go pretty small here. Okay, we have where the light is coming from. It's called the incident ray. Okay, the angle theta 1 is measured as compared to the normal to the surface. Okay. So here's the surface. Normal would be 90 degrees from that. It is not measured from the surface. It's measured from 90 degrees to the surface. Super critical. As a kid growing up, I had this sense that it was always against the surface. And so when I was in physics, I struggled with that a little bit. Theta 2 will also be measured against the normal, okay? So we're always measuring against the normal, not against the surface. Whether the light's coming in or out, same thing. Now, there is some light that will be reflected. It always is a little bit, but for the most part, it's going to be refracted and go down in. So that was called the angle of incident and the angle of refraction. And those are our two angles. Now, Snell's law says there's a relationship between these two that has to do with the way that light travels. Now this is really neat because when you watch the light from this girl's legs or whatever, okay, and you're trying to figure out where her feet are, think if this is not necessarily the same question, and you shouldn't do this to a girl, but if you were going to spear fish and you're looking down at the fish and you're trying to decide where do you aim, okay, you have to understand what it looks like to you because your brain perceives light as traveling in a straight line. It looks like her feet are basically right here where her kneecaps are. It's like she's much taller. So the water looks shallow, Or she might look like she has really short legs. One of the two. Kind of awkward looking. But what's really happening is she's down here. So you would always aim below her feet, knowing that it's actually below her feet is where her feet actually are. It's kind of weird to say that your feet are actually below your feet, but it is what it is. Alright, so that's this concept that we're dealing with refraction. Now Snell's law is what we're going to live off of when it comes to solving a lot of these problems. It says that n1 times the sine of theta 1 equals n2 times the sine of theta 2, which means if you know what material you were in to begin with, and you know what angle of light came in at, you should be able to find out, based on the material you're going into, what the angle of refraction would be. So you can kind of see, as light comes in, it's going to bend. Now coincidentally, these angles will match because of the AIA theorem, alternate interior angle theorem from geometry. And so then we have, theta B here. Theta A would match theta A, and so on. So we can use Snell's law to say what angle is this light coming in and out at. So let's look at this is kind of a simple problem that we can kind of practice together. So let's say that we had one of the really common ones is water and air. So we'll just do that, H2O and air. I'm just going to let you know that N for H2O is 1.33, so I don't have to go back to the book. And the N we're going to use for air is 1. Let's say that I have a flashlight and I shine a beam of light that's going to strike the surface at 60 degrees to the normal. And the question is, what angle does it come out at? Now, one of the things that you need to understand is that if light is speeding up, okay, so this way is speed up. If it's speeding up, you're going to get a bigger theta here. Okay, that theta would start to slide down towards 90 degrees, and that would mean that it's speeding up. If it's going this way, it's slowing down. Now what you have to remember is that the lower the n value, the faster the material. So we're going from a low n value of 1 to a higher n value of 1.33. That means the speed of light is slowing down. So we should expect this theta 2 to be less than 60 degrees. Let's grab our setup here. N1 sine of theta 1 equals N2 sine of theta 2. Now you may or may not see this, but if you really wanted to know where does Snell's law come from, it's the law of sines. You can sort of divide N2 over, divide N1 over, and you get something very similar to the law of sines. So if you're wondering, Mr. Welch, where's this all coming from? Back in geometry and algebra 2, we learned about law of sines, and that's the foundation for Snell's law. But let's just go ahead and run with it. N1 was 1 times the sine of 60 equals 1.33 times the sine of theta 2. So I'm going to divide by the 1.33, say that sine of theta 2 equals, and I'll just use, let's use Desmos as our quick calculator. Remember, if you're using Desmos or some other piece of technology, make sure your calculator is in degree mode. Desmos always defaults back to radians. So I'm going to go ahead and use the sine of 60, and that's supposed to be divided by, oops, I guess I'll do it again. Sine of 60 divided by 1.33 equals, oops, I do that all the time, okay, equals 0.6511, okay. I'm actually going to go ahead and put some big parentheses around that. There's a reason. In our problem, okay, it's at 0.6, blah, blah. Okay, I still have to get theta 2 alone, which means I need to apply a sine inverse or an arc sine, depending on what you've been told to call it, to that value. So we're going to go back into Desmos here real quick. I'm going to come over here to the left, and I'll use my sine inverse on that to get 40.6 degrees. And so it turns out in this problem that theta 2 is 40.6 degrees. That is less than 60, which is what we expected. Now we can make predictions about where the light's going to go. Now the second thing that we talk about in this section of work is what's called total internal reflection. There's a video that I shared here on OneNote that has that attached with Snell's law, and there's some really cool demos you can kind of take a second and look at. But back in the book, when we learn about total internal reflection and fiber optic cable, there is a tipping point when we make this theta 1 big enough, if we make it big enough, that we can actually get the light to follow the surface. Okay? Rather than going out, we cause it to bend all the way to 90 degrees. When we can get it to bend to 90 degrees, okay, then we have what's called total internal reflection. This is what's called the critical angle. If we go bigger than that theta c, whatever that critical angle is, then the light will bounce inside of the original material. What that does for us is it provides us a way of communicating information through fiber optic cable and other types of things like that, where we want to keep the light inside of a single material. This is actually a really cool thing that you can do. If you get a laser pointer, I would strongly encourage that you seal it, maybe double seal it in some Ziploc baggies, keep it dry. But you can actually go out at night to a lake or a pond and put it underneath the water. Now, you can technically do it in anything. I think it's kind of cool to be outside in the rivers and lakes, but you can do it in your bathtub too. You take that laser pointer and you put it under the water and you point up towards the top of the water. If you change the angle, you can get it to bounce back and stay inside of the bathtub or lake and not actually exit the water. Really cool thing. A really cool experiment that you can do there on your own with internal reflection. But one of the big questions is, what is the angle necessary to create the sense of total internal reflection? Okay, and so what we find is that if we take, let me go back to, we take Snell's law and we tweak it just a little bit, and we let theta 2 be 90 degrees. Okay, well the sine of 90 is 1, right? So what that ends up with, if we solve for sine on so sine of theta, we'll call this C, equals N2 over N1. This is our total internal reflection rule. Now, as a side note, we have to identify a couple of things. First, the sine of theta is only valid when it's equal to something less than 1. You can be equal to 1, but you can't be greater than 1. So if this fraction was like 1.5 over 1, this doesn't work. Okay? There is no way to create total internal reflection when the light is speeding up. Okay? You have to be going from I've reversed that. You cannot do it unless the light is speeding up. Because you see how slowing down caused it to come closer to 90 and get a smaller angle? We have to push this all the way down to 90, which means we have to be speeding up. Okay? To speed up, that means that the N2 has to be lower than N1, and that's how this stays under 1. So if you want to know the critical angle for a material, like for instance water and air, okay, to do that, the sine of theta c for air, water, you would have to go from water to air. That's why I said you have to put the laser pointer in the water. So my N2 would have to be 1, my N1 would be 1.33. If you're ever given this scenario and it's in reverse where your top value is bigger than your bottom value, then it's not possible, and you don't even have to worry about it. But this would just be a sine inverse. So I'll go to Desmos real quick. Clear that out. Just do a little sine inverse. Clear that out. Start over. All right, functions. Sine inverse of 1 divided by 1.33 at 48.8 degrees, or 49 degrees roughly. if you can get your angle set up to be at that 49 degrees, 48.8 degrees, the light will not leave the water. And it'd be a really cool experiment for you guys to go out and try. Just again, be careful. Don't ruin a laser pointer by putting it under the water. Make sure it's protected appropriately. And yeah, it'd be a really cool experiment you guys should go do. I've done one similar to it. I just think it's really cool. Watch the other video that has the demos if you have questions about it or what it looks like. And good luck, and we'll see you during chats.